Hello chaps and chapettes, and welcome to this video on energy. I'm just going to have a sip of coffee, even though this is actually going to give me no energy at all. Ugh. So what we're going to look at now is energy, and that cup of coffee I just drank actually has, okay, it does have energy in it, but it's not going to give me any energy, it being black coffee. It will have a tiny amount of energy, but not actually anything that you would really be finding useful. So what we're going to look at now is we're going to find out what a definition for energy actually is. And then we're going to know what types of energy there are. And we're going to be able to use the base energy formula. Now, there is a challenge attached to this one. I want you to look around the room around you and identify all the different types of energy that are there. Identify most of the types of energy that are there, because if you try to do all of them, you will literally be there forever. So just some of them will do. And write them down in the comment section below. So what we need to know is actually a definition for what energy is. And it's not the kind of thing you might expect. It's not the sort of get up and go and get out of bed and ability to, well, actually it kind of is the work you can do. You know, I'm going to cycle back on this one, come back to it later. There are two words that you need to know definitions of if you want to look at what energy actually is. And the first one is to understand what a system is. And a system is an object or a group of objects. Now, the best example I can give you that is one that you've been using most of your life. The solar system. It is a group of objects around the sun. So it is the solar and system. It's the system of things around the sun. You are a system because you are a collection of objects. And I know you're thinking you are a single object yourself. Well, yeah, you could be classed as a single object, but you are also a bundle of different ones, all kind of stuck together. Not only are you a collection of sort of squidgy organs and, you know, skin and stuff, even those organs and skin and stuff are kind of made up of tiny little objects called, well, cells. And even those cells are collections of even tinier objects called atoms and so on and so forth. Basically, you class yourself as a single system or a system of systems. But you are a system, and that's just the definition of that thing. The second word is energy, and there's a reason you need to know what a system is, because energy is the ability of a system to do work, as in the ability of a system to actually do something functional in the world. It is what allows an object or a system to actually change some of its properties, either by moving, like changing its physical space, by changing its shape, by changing its temperature. Energy is the capacity of that system to make those changes. Now, what this kind of boils down to actually is basically moving particles. But there are some types of energy that you need to know, and you will be familiar with these ones from Key Stage 3. We're just going to make sure that you remember what they are going into GCSE. So let's go into what they are, and I'm going to show you what each individual one is at the back of my classroom. So before we go there, make sure you hit the like button so that you can find this video again later on, and so that the YouTube algorithm knows where I am, and so that more people can find out where these videos are. Anyway, come and join me at the back of the classroom, hit the like button on the way, and I'll see you there. Right, now, just like everything in physics, looking at energy is actually just an excuse for me to play with a bunch of toys. So that's what we're going to do. Starting with kinetic energy. Kinetic energy is the energy of moving stuff. Anything that is moving has kinetic energy. So right now, this as a system has, no visible kinetic energy. It's a little bit more complicated than that, but basically if we start moving it, it's got some kinetic energy. And the factors that go into kinetic energy are both the velocity it moves at and also the mass of the object as it moves. And those are your factors in kinetic energy. Where this gets a bit complicated is that pretty much every particle in existence has some kinetic energy. And taking this as an example, even though the ball looks like it's not moving right now, all the individual atoms in there are actually bouncing around like crazy. So this thing, even though it might not look like it, has some kinetic energy, at least on the inside. We'd call that internal energy of the system or the object. Okay, so there we go. Most of the stuff you'll deal with in GCSE will deal with the kinetic energy of actual moving objects. So if it's stationary, it will have 0 kinetic energy. If it's moving, it will have some kinetic energy. And, well, there you go. Right, now this might not work, but this is very much related to kinetic energy. This is sound energy. And I've just realized I put my slinky down. Hang on 1 second. Right, now sound energy is one of the very many ways in which energy could be wasted. Whoa, jeez, that's loud. One of the many ways in which energy could be wasted. And it is the energy of things that have sound. Now, as you can probably see, sound energy is actually just kinetic energy, but like a specific type. Basically, we're dealing with movement of particles. And in this case, we're dealing with movement of particles in a sort of wave form, which is being transmitted as easily understood sound. I don't know if you can see that moving up and down. I can certainly hear it moving up and down. If I just slow it down a bit so you can see that. There we go. So basically, sound energy, it is kinetic energy, but you are expected to recognize it as one of the ways in which you could lose energy from a system. Okay, never play with matches, unless you're a physics teacher, in which case, well, that's one of the perks of the job. So what we're looking at here is heat energy, and well, here we go. There we go, and that's heat energy. Basically, it's the energy of stuff what is hot. And the thing is, everything with a temperature will have some heat energy. And when I say anything with a temperature, I mean anything. This includes things which you think might not have much temperature at all, like ice, which will be colder than you'd expect, but they still have a temperature above absolute zero, and so they have heat energy inside them. The idea here is that the particles inside your substance are all bouncing around really, really quickly. I know it doesn't look like they're bouncing around here, but they're vibrating really, really quickly in place. And because of that, you're going to experience some form of heat or temperature from the object. And if you're thinking, well, doesn't that just mean that heat energy is the same as kinetic energy? Yeah, you'd be right, actually. This pretty much is. But you are expected to know it as a different sort of energy dealing with the temperature of objects as opposed to the things moving around. Now this is where I'm really hoping that I've actually got a nice little video of electric sparks from my Van de Graaff generator. If I don't, all I'm going to do is point to this thing and say, look, electrical energy, because, well, that's all I've got. But electrical energy is essentially the movement of charged particles, or at least the movement of charged particles. Or you could look at it another way as being the potential between charged particles, which is where it gets a little bit complicated. What you need to understand right now, though, before going into more electronics, is that electrical energy deals with the energy of, well, charged particles. And there we go. Now, we have another energy type to talk about, and that's going to be light energy, which is why I get to play with matches again. There. So we can see that this object is emitting light, and that's going to require some energy. Happily, you don't have to do much in terms... This is going to burn my finger, isn't it? There we go. Happily, you don't have to do much in terms of actual equations for light energy. That comes in an A-level, really, although the equations aren't as difficult as you might think. But light energy is, in fact, the energy of objects which are luminous, as in they emit light. And, well, there you go. Light bulbs are emitting light energy. And you kind of know that you can pick up on this energy because of things like solar panels and solar cells. And actually, if you stick your hand up towards the sun, you can kind of feel your hand burning a little bit. If you're in any other country apart from the UK, where it is beautifully not sunny right now, even though it is in the middle of the summer. Wonderful days. Okay, ready for this one? Gravitational potential energy. Basically, if you have something above the ground and you drop it, it will start to move, which means that there is some stored energy in here. This is going to be the first of our potential energies. And gravitational potential energy is a very easy one to get. Basically, anything above the ground, so you have a change in height, then you have some gravitational potential energy. The real explanation for that is that you are further away from the gravitational well, or the gravitational field created by the Earth, and what the two masses of the Earth, well, table and the Earth below, and the mass of the object want to do is they want to attract to each other. And if you separate them, then you need some energy to separate them, so that's gravitational potential energy. Of course, if you let it go, then, they come together. And that's gravitational potential energy. Now this is elastic potential energy, but I don't think a slinky in this case is the best example of it. Basically, if I start to stretch this, it takes some energy to do it, but then the energy is stored inside the spring. This is elastic potential energy. So if I were to let go of this, then it would snap back. Basically, the energy stored in the spring as elastic potential energy is then expressed as a force, which pulls these things back together again. Now you have a variety of ways that can be used. This is a children's toy. And if there's one thing I love about physics, it's that you get to play with children's toys during lessons when talking about, well, the mysteries of the universe. So here we go. You wind this up, and you're putting elastic potential energy into the device. And if you were to let go, then the elastic potential energy is then released as kinetic energy. Wonderful. You find this actually in things like clothes and other stuff. Your clothes will have a little bit of elastic qualities to them, so that when you stretch around and move around your body, they will snap back to the shape at which you want them. If you were to wear things like sports clothes and things like that, you want to be able to minimize the effects of drag and all that kind of thing, and you'd like it to actually snap back to your body. This is where elastic potential energy comes in handy. If you move around your body, you're going to be adding elastic potential energy into your clothes, and then as you move back to your original position, that elastic potential energy will wrap the clothes back to around your body, and therefore you're not going to have any bits flapping around everywhere. So there you go. And he gets his matches out for a third time on this one. This is chemical potential energy. So you see this tip here. This is made up of a bunch of chemicals that if you were to apply a little bit of kick-starting energy, then you would release all the chemical energy inside this thing. Chemical energy is another potential energy. But again, happily, you don't have to worry about the equations for that. That tends to be the purview of, well, the subject chemistry. Well, this is just highlighting that chemistry is in fact a small subset of physics, because they only deal with one of the types of energy in there. Although honestly, they look at kinetic energy as well. Forget I said that. Chemistry is not a real subject. It's basically physics, just deals with a small part of it. So chemical potential energy is energy locked up inside molecular bonds between different atoms inside these things. And if you were to break apart those molecular bonds, then you release some of the energy inside. You will use this in things like matches and any fossil fuels that you burn. You will also use this in things like this, acid or alkali batteries, where you separate your ions and then they are allowed to come back together again and start currents moving. You will have experienced this at some point today, or at least I hope so, in the form of food, where you will have taken some carbohydrates or fats or things into your body and broken down the bonds between the carbohydrates, releasing the lovely energy in there so that you can watch YouTube videos and hit the like button for me. This is nuclear potential energy. I can't show it to you, or at least I kind of am showing it to you really, because all these things around you it's all actually made of atoms, which means that everything here has nuclear energy sort of locked up into it. So if I just get rid of this symbol, here we have a standard atom. Okay, there we go. I'm going to have some electrons whizzing around the outside of this one. There. So this is an atom, and you can see that the nucleus here is made up of some particles, and the particles are kind of stuck together. Now, if you were to break these things apart, you would release the energy which is used to bind these things together. So if you're splitting them, that's called, if you're splitting them, that's called fission. And you'd usually do it with an atom much, much bigger than this, something nice, big and chunky like uranium. You break apart that thing, And there's so many like little bonds in between the protons and neutrons of a nucleus that they produce a lot of energy as they come out. Not nearly so much as fusion. So fusion here, fission, that's strange. Split, and then stick. So fusion is where you take two small atoms and you stick them together. And through some complicated physics, which I'm not going to go into now, you actually get more and more energy coming out of these things. Kind of, actually. There's a small little tipping point between, well, basically an ion, where you gain energy if you fuse smaller atoms than iron up together, and then you start losing energy as you fuse more things together to get larger and larger atoms. With fission, you gain energy splitting big atoms all the way down, and then you lose energy trying to fission them past iron again. But that's a lot of A-level stuff in there. You don't need to worry about it. And there you go. This is nuclear potential energy. It's the energy which is locked up inside the nucleus of atoms. And, well, you've just got a lot of energy there. Now, those are all different types of energy, and that's fairly straightforward. And they pretty much all have their own individual equations to describe them, their own individual formula to describe what they are. I'm going to give you the most basic version of energy, or the most basic version of the energy formula. And it's really straightforward. It's basic logic, actually. It's something that you'll know almost instinctively. So come and join me in the back. What we'll do is we'll look very briefly at the theory behind it, and then here's the formula. So what we want to do is quantify the amount of energy we're using. And what we get is an equation like this. Energy is equal to force times distance. And I just realized that's not really enough space on there, but force times distance, or E equals FD. And that's your basic formula for energy. Let me just explain that to you. So what we're going to do is explain how energy works, or at least how to quantify energy, by using this object here. Now, to push this object across a certain distance, I need to exert a force on it to counteract the resistance of the table and things. And that takes some energy to do so. Remember that energy is the capacity of the system to do work. So as I apply a force, I am using some energy. So how can we make this bigger? Well, what we can do is we can increase the distance I push it. Moving the object there takes less energy than if I were to move the object there, basically playing the distance. We can also change the object. There we go. Now, this is a bigger object, and it takes more energy to move it there. Oh, crikey. Than it does to move it. Than it does to move this one here, which is relatively straightforward. But if I were to move it over there with more distance, it takes more energy. I need to go to the gym. And that's pretty much why we have this equation here. If you've got an object which requires more force to push, you're going to need more energy to do it. If you're pushing it through a greater distance, you need more energy to do that. So the basic formula is energy, or work done, is force times distance. I'm just going to write that down there, energy or work done. This is important. You need to know this one so I can tell you a terrible joke in the next video. Okay, so from this video you should know a definition for energy. You should also understand that there are different types of energy out there, and that they actually all kind of boil down to just the one kinetic energy, but we'll leave that alone for now. And you should also be able to use the base energy formula. I'm really looking forward to the challenge task today. I'm wondering what unique forms of energy you've got around you right now. As in, have you got any unique forms of elastic potential energy? Have you somehow managed to unlock the nuclear potential energy in your room, and have you caused a small fission or fusion explosion because of it? I want to know these things, so let me know in the comment section below. And if you haven't done so already, make sure you like, comment and subscribe, and I'll catch you in the next video.